Second lecture of your PSI year, and welcome to Waterloo and PI, everyone. So I'm Maïté, but you should already know that. We all met yesterday. So we will have 6 lectures together to talk about this really beautiful topic, which is Lie groups and Lie algebras. Of course, group theory is a really huge topic, so we won't have time to say. I won't have time to say much, and I'm mainly going to focus on Lie groups because these are the groups that you are going to be interested doing physics. But for today, I'm not going to talk at all about physics or about Lie groups. I just want to start with just 2 sets of numbers and play a bit with these 2 sets of numbers. So I'm going to start with this quite simple set of numbers. And let's write the second one here. And another one, which is almost. And we are going to play a bit with these 2 sets of numbers. And of course, I'm going at some point to add some structure to talk about groups. But let's start with this set. So we can consider this set of 4 numbers as the set of integer modulo mod 4. Okay? So how do you write this? Use this notation. So I don't know if you're already familiar. So Z is, of course, the set of integer. And here you have some equivalence class relation, which tell you that you consider only these 4 elements. Of course, we can write now, and this is, we are going to consider here the addition as operation. So let's write together the addition table. Okay, so here it's a plus, and I'm starting with this element, and I want to add all of them together. So of course, if I add 0 with any of the number, I keep the same. So now let's go to the second line. So I add 1 to 0, so I get 1. I add 1 to 1, I get 2. I add 3. And then 1 plus 3, what do I get? Yeah, 0, okay? Because it's 1 times 4, so it's 0. So here it's really the set of numbers which can be written. So any multiple of, you forgot, yeah, I'm going to write that later when we introduce the equivalence class relation. And okay, so now let's do the same here. So 2 plus 0, 2, then I let you do it, okay, 3, and then 2 plus 2 you get 0 again, and 2 plus 3 you get 1. Okay, so you understand. So 3, 0, 1, 2. So this is the addition table for this set of numbers. And now this might seem pretty pointless now, but let's rewrite it using this symbol. Instead of the addition, I'm going to use, yeah, surprise, everything. So instead of the addition, I'm just going to use this symbol for the moment. And of course, the 0 here is going to be, so this circle. This is my operation. The 0 is just the E element. We're going to see that it stands for identity. And then 1, 2, 3 go to A, B, and C. So these are exactly the same table, but just written in a different way. So why do I want to use this table? So this is going to become clear in 1 minute. So now let's focus. So right now we haven't done anything complicated, okay? These numbers are very familiar to all of you, of course. And now let's focus on this other set of 4 numbers. It's almost the same, except that it's 1, 2, 3, 4. And this is called the set of units mod 5, okay? And this is a kind of modulo multiplication group that we write like this. And now we need to specify that this is for the multiplication, so we add this notation. So this set of numbers can be seen as this group. And so if now again, I do the same small exercise, meaning I'm going to write the multiplication table now for this, all this number. What do I get? So of course, 1, if you multiply 1 with any number, it remains the same. So now let's go to 2. So 2 times 1, it's still 2. Then it's 4. Then 2 times 3, what do you get?
1.
Are you sure? 2 times 3, yeah, sorry. Or what? Yeah, let's write. Sorry, guys, I'm going to, yeah, you're right. So I want, in fact, to write it the other way, because I want to show you something then. So let's invert these two numbers. So 4 and 3, there is no, I can choose the order I want. Okay, so 2 times 4, now what do I get?
3.
Yeah, very good. And 2 times 3, 1, as you said. Okay, so now it's, again, 4. Then 2 times 4, again, it's 3. 4 times 4.
1.
Yeah, good. And 4 times 3?
2.
Good. You're getting faster and faster. Okay. So now, again, 3. Then what do I get?
2.
Okay. So can you see, what can you say about these two tables? Yeah. Okay. So if now, instead of doing here, if I have this map, so the multiplication is this operation. And then the 1 is my identity element. Then A is 2, B is equal to 4, and C is equal to 3. It's exactly the same table. So in mathematical language, what do you say? We can say that this group, Z over 4Z, with the addition, and this group, Z over 5Z, with the multiplication, are isomorphic groups. But so now let's introduce, so first here I use two words, isomorphic groups. So since I don't really know what is your background in math, okay, I'm going to go through all the basic definition to start with, and then of course we're going to go to more complex things. But so of course here I need first to define the notion of group, and then I'm going to define really exactly mathematically what this means to talk about isomorphic groups. So let's write the definition of a group. So first definition. So a group G. So a group, so it's a set, as you said, as we have seen. Here we consider two different sets, but you need to define an operation that we call with binary operation. So sometimes in the literature it's called the multiplication of the group, but you see that here multiplication is really the meaning. In this case, multiplication is in fact the addition in algebraic in algebra. And here it's really the multiplication of number, okay? And depending on which object you're talking about, it can be different operation. So here I'm not using this word of multiplication, even if you can say that in the literature, just to avoid some confusion. So it's an operation. And which satisfies the following property. So what do we have? The group is closed under the binary operation. So So is that clear to everyone? This means that for any G1, G2 in your group, G1 with G2 is also an element of your group. Okay, so is that the case for the two examples we looked here? Of course, since you have the multiplication table or the addition table, you can see that adding elements or multiplying elements together, you're still in your set of numbers. Okay, so this is satisfied for the two examples we looked before. Then this operation has to be associative. Okay. So your operation is associative. This means that if you take 3 elements, the order you're doing your operation is so let's go back to the two examples we looked at. Of course, here it's associative because the addition and multiplication of numbers are associative. Okay, so you just have to say that. Then the group has an identity. So this means you have an identity element. So this means it exists. So everyone is familiar with this kind of symbols? Yeah, sure. Okay, great. That's that for any G in G, you have that okay, so what is my identity element here? 0. And here, of course, for the multiplication, it's 1. Okay, so this is quite trivial here. Then the group has an inverse. This means that so for any G, okay, in your group, it exists an element G1 minus 1 such that when you combine them with your binary operation, you go to your identity. And of course, using here the tables of multiplication or addition of the two sets we consider here, you can find the inverses for all elements. So for example, what is the inverse in this case? What is the inverse of 1? Yeah, very good. So here, inverse of 1 is equal to 3 because you have 3 plus 1 equal 1 plus 3 equal 0. Okay? So you go back to your... So here you can easily see that indeed these two sets with these two operations, either the addition or the multiplication, are groups. Very good. So now let's clarify what is the meaning of isomorphic. And then so you can already guess, roughly isomorphic means that the two groups have the same algebraic structure, okay, as you can see from this example. So more precisely, if you have so two groups G, and we will come back on this definition. So here it's quite isomorphic, and we use usually this notation. So if there is during the tutorial this afternoon, you will have to find some explicit isomorphism between these two groups. So I'm not going to give you more detail here. So it's a one-to-one correspondence between the elements, which is preserved under the multiplication group, the group multiplication, okay, or the binary operation. Under group Okay, so these are the first two definitions I wanted to give you, so basic one. Now I just want you to spend a few times on this definition and let me know what you can say about this set with this binary operation. Are there groups or not? So I'll let you just 1 minute to think about it and to say yes or no. And if it's no, of course, let me know why. This is the multiplication. And here, the set of negative numbers with multiplication. Okay, so I let you 1 minute to let me know which one of these is a group or not. Okay, and if not, let me know why. So once you're done, you can compare your result with your neighbor. I remind you that here we are going to try to encourage as much as possible collaboration. So let's just share what you found and try to convince your neighbor, if you don't have the same answer, why you think you're right or not. And then I'm going to say something about yeah, so this means that it's all real number except 0. Okay? Yeah. So you can compare your answer okay. So, is that a group?
Yes.
Yeah. Is that a group?
Yes.
Yes? Who said yes? Okay. Who said no? And why? So you need to convince your...
It's not associated?
Yeah, it's not associative, okay? If you take the subtraction is different from... how do I write this? Okay? Not associative. Good. Then is this one a group?
No.
Why?
0 has no.
Very good. So everyone agree on this one. So this was no. This was no. So 0 has no inverse. This one? Yeah. And this one? And why? Yeah, it's not closed under multiplication. If you take two negative numbers, you multiply them, you get a positive number. So you're out of your set. So here it's no. Okay, very good. So this was just to let you think a bit about these different properties that you need to have a group. So now just I will come back on the motivation, especially from the physical point of view, but just now let's take a break and see why we are so interested in group theory. So group theory is related to symmetries, and we say that an object is symmetrical, of course, if some transformation leaves the object unchanged, okay? So if you take, for example, an orange, you can see that I can turn this around its axis, and it remains unchanged. Okay, so this object is symmetrical. Of course, I could also peel this orange, and what I have as a continuous symmetry now will be broken to a discrete symmetry. Okay, you can imagine that. I don't have to do it. Everyone knows how an orange is inside. And of course, there are many everyday objects which are symmetrical, in particular food. So you have pancakes, donuts, everything has some symmetry. Another interesting object that everyone knows that is also, in fact, even interested for mathematicians, for not now anymore because it's solved, is this Rubik's cubes. Everyone knows this game. Okay, so you have 6 faces, 27 small cubes, the cubies. And so how do you play? To play the game, you can perform the following move. So you can turn you choose one of your face. So you have, let's say, this is the front, top, up, down, left, right, and back. And you turn one of them clockwise or counterclockwise from a quarter of a tour. And then you get to a new configuration. And of course, you can check that all these moves are enough, even more than enough, to get all the possible configuration. Okay, you have many choices. And so let's go back to my initial configuration. And in fact, this from all these moves from a groups. Okay, the Rubik's cubes groups. And why is that a group? So to generate all configuration here, so this kind of move is what we call a generator. Okay, so I'm going to come back to a generator, and you can use only these generators to get all the configuration of your group. So I'm going to give you in a minute what is really the definition of a generator. And so now the collection of all the move, as I said, from a group. Why? The binary operator here is to perform 2 moves in a cycle. Okay. So you see that here I can choose to do my move M1, and then I will do my move M2, and this will define my binary operator. And of course, the identity element is when you do nothing, you just stay like this, and you can really easily see that each move has an inverse. Okay, so here I do this first move, I'm in this configuration. I do the other in the other way, and go back to the initial configuration. So it's really a group. And so today we are going to remain with these 2 examples we have, these 2 sets of numbers, and these Rubik's cubes to try to introduce many definitions. So now I'm going to give you definition, and we are going to work with these 2 groups and these Rubik's cubes to try to understand what this definition really means. And tomorrow we will go to physics and talk a lot about why we need to have Lie groups and everything, but at least you will have some already quite abstract definition in some specific examples that you can really see. What is interesting with these 2 sets of numbers is that since there are only 4 elements, you can really figure out what this means explicitly. And with this example, what is interesting is that it's still a discrete group, but with many, many configurations. So we will have to introduce the notion of subgroup and stuff like this if you really want to study it in an efficient way. But so before going to all this definition, I just use the word generator. So I want to give you now the definition of a generator. And then we are going to move with more definition. So here, so this was just why, and now some more definition. So of course I'm going to, I don't know, do you all have your PI address now working? Not yet. Okay, exactly. And so you don't have access to the wiki page yet. But I'm going to post everything, so hopefully by tomorrow or the other thing. And all the lecture notes will be there. Okay, so the definition 3 now is the definition of generator. So we consider a group G and S just be a subset. Okay, I'm not introducing the notion of subgroup yet. And we are going to say that S generates G, or that S is a set of generators of G, is if every, so you can choose the way you say it, every element of G can be written as a finite. So here I'm using the word product, but of course product has to be understood as you consider the group operation. So here of elements of S and their inverses. Okay, and so then usually we write G like this. We can use this notation. Okay, so we have seen what are the set of generators for the Rickaby cubes. Now, what is, if you consider the set of all integer, what can you say? What is generating this? How many generators do you need? Yeah, what is the generator? Yeah, very good. Okay, you can, all number can be obtained like this. And what can you say about our set of 4 number here that we use with the addition here? What is the generator here? Okay, yeah, very good. So you see that you have to be careful when you have the set of generators. Doesn't mean that you know which group you're talking about, okay? Because you see that these two groups are quite different, but they are generated by the same, only one generator. And here, so this kind of group where you have only one generator are what we call the cyclic groups. Okay, so here let's maybe add the definition of so we said that a group if there is G in that you can write. Okay, so these two groups, Z and Z over 4Z, are cyclics. Okay, so another interesting characteristic of all the groups we've mentioned up to now, except the rotation group that I just very briefly mentioned with my orange, are that, what can you say something about, what can you say about the binary operation that we use here? Here I can do 3 plus 1 and 1 plus 3 or any other one, and it's always the same. So what do we say here when it's this case? Or here, the multiplication, you can multiply 1 with 1 times 2 is equal to 2 times 1. So how do you say? Commutative. Sorry? Commutative. Yeah, it's commutative. And then do you know when the binary operation is commutative, how do you call the group? Abelian. Yeah, okay, very good. So here we only, oh, sorry, I'm getting, okay, so abelian group. So I'm going to, well, maybe I shouldn't do this. I'm going to keep the definition of a group. So we don't really need this one. So yeah, just to make sure that it's clear to everyone. So when the definition 5 so an abelian group has the property that its binary operation is commutative. That is that if you want that if G1 for any G1 in G, then we said that G is abelian. And another common feature between these two groups we mentioned here and the Rubik's group is that there are finite groups, okay? Because they have a finite number of elements. And for a finite group, you're usually interested in the order of the group, which is the number of elements. So you can see that these two groups here, that was that for, and I don't have the other one, but this one that we mentioned before, what are their order? They are both of order 4, okay? There are 4 elements, so it's the order of a group. So which other definition do I want to? But so, yeah, indeed, so these two groups have order 4, but then the Rubik's groups has a much bigger group, okay, with much larger number of configuration. So it's not always easy to, an easy task to study this huge number of configuration. So what can be useful is to restrict the problem. And for example, instead of looking at all possible moves here, you could restrict only to this kind of move. So the move of this phase going to the, only the left move, for example, okay? And then this means that you will be looking to, this means that you will be looking to a subgroup, okay? So what is a subgroup? And this is something quite common that you want to do in math or in physics when you have a very big group, G. Sometimes you start to understand small pieces of it. And for this, you need to introduce the notion of subgroup. Okay, so what is a subgroup here? Okay, so definition 6, a subgroup so we said that A is a subgroup of G. Of course, so this means that first you need to have a subset of G, and that then A is also can be seen as a group, so it's also closed under the operation, so the group multiplication. And the inverse of every element exists. So here it's again really the definition of a group. You really want A to be a subset. And every group so here the set of which example can we have? The set of even integer is just a subgroup of the set of integer with the addition. And the identity, of course, each group has a trivial subgroup that consists only of the identity. And so, in fact, we have two trivial subgroups that we call. So each group has the identity and the group G itself are what we call the trivial subgroup. Okay, so we see that this is going to be important. This notion is going to be important when we introduce the notion of representation and irreducible representation. But many other groups have non-trivial subgroups, and we can use a subgroup to divide up the element of a group into subsets that we call the coset. So what is a coset now? And so any questions here? So it's going to be a lot of definitions that we are going to use then during the next lecture, which are very general, which are not only related to abelian Lie groups. So hopefully, so now you can use really the notion of coset to divide up the element of the group. Okay?
I have a quick question.
Sorry?
The inverse doesn't have to be in the subgroup, it just has to exist. So you said for the identity.
No, it has to be. Yeah.
Inverse.
Yeah.
Does the inverse have to be in the subgroup?
Yeah.
And the fact that the identity must be in the subgroup is included into the closed under the group multiplication, or should we like add it?
Yeah, so since we have this exist, and this means also that indeed the identity has to be in the, so, yeah. Yeah.
Can you have a subgroup where you can pick a different identity than the original subgroup? Oh, no. 'Cause you
No.
need to- okay.
No, because you keep the same, you keep the same group multiplication too, okay? So usually for a given group multiplication, the identity is going to be given with this. For example, with numbers, if you have the addition, the identity is going to be always a 0, okay? It can be all the set of all integer or z over.
Maybe can I rephrase something? Like, can you have a group with two different identities?
No, and in fact, you're going to, maybe I changed the question, but so one of the questions with, of the tutorial for this afternoon was to show that a group has a unique identity, and I think I changed it to show that a group, each element has a unique inverse in a group, but it's the same kind of proof. So you're going to prove that, and the proof you're going to do will be really similar if you want to prove that a group has each group has a unique identity, okay, element. Okay, good question. Are you okay with all these definitions? Okay, so let's try to move up with 2 or 3 more, and then we're done with this definition for today, or at least this kind of definition. And then we're going to go to the notion of representation, okay? So what is a coset? So I'm going to give you the definition of a left coset. So the left coset, so you need to have a subgroup here. Let's call it H now. So in a given group G, and the left coset of the subgroup in G is a set of elements from so by the action of H on the right on a given element of G. That is, so maybe I don't need to write this. Sorry. I'm just going to write everything with verb. Sorry, guys. Oh. It's just so the set of element of the form GH where G is fixed, okay? In G. And this is an element of, and of course you would have the right coset would be the action on the left by a group element. So here what I said, it's a left coset, and the action is on the, the action by H is on the right of the G element. Okay? And of course you have the same definition for the right coset. So now let's consider, so this set are the multiple of 4, so you get -8, -4, 0, 4, 8, etc. So this is a subgroup. Let's give you a definition of course, the set of integer with the multiplication. So now, what are the coset? So here, since it's abelian, you're not going to talk about left or right coset. Okay, it's all the same. So what are the coset of So I let you 1 minute to think about that. How many do you have? So here, yeah, to be more clear, maybe. So here is really all the elements given by the action of H on a fixed element here on the right, on a given element of G, okay? So here, your H is this set, and you look at your group. So how many cosets do you have? 4. Okay, very good. So, and how do you write them? So here, okay, are the cosets? And of course, since here it's commutative, you don't have any left or right coset, okay? Is that clear to everyone? So then, of course, if you try to build 4z plus 4, you go back to this exact set. Very good. Okay, so now we are going to go back to this maybe notation that I'm not sure was clear to you, this notion of quotient space. But before that, if you want to have a quotient space, a quotient group, sorry, the quotient space is always defined by the quotient group. To have a group, we need to talk about what is an invariant normal subgroup, okay? So here, this, so it's definition 8, invariant normal subgroup. So what is an invariant normal subgroup? If it's for 2G, you have that, so the right and left coset, then H is an invariant subgroup of G. So sometimes you forget about the normal. So of course, the identity and the group G are always invariant normal subgroup. And then if a group G has only, if G, so let's see some example. If G is different from the identity group, just the identity element, and has only E and G as normal subgroup, then we said that G is simple, okay? So if you see the definition that a group is simple, this is the meaning of a simple group. And here you could check that, of course, is an invariant of, and because of that, indeed, when we use this notation that we introduced before, which is in fact the notation we use when you build a quotient group, okay, or a factor group, then this exactly, since 4z is a invariant subgroup of z, then this is really a group, okay? It is not always the case. So I'm going to give, yeah, you have a question? No, that's fine. Any questions here?
Did we define exactly what? Oh, never mind. That was a question. Never mind.
Okay, great. So just the last definition of which is going to explain this notation we introduced, okay, which is really a notation you are going to see quite often when you are going to talk about group. This notion of, because it's in particular in physics, we often use a quotient group. So maybe I can just And so here, the last definition is of a factor group or quotient group. Okay. So if H is an invariant subgroup, invariant normal subgroup, then which is given by where you consider all G which belong to is a group. Okay, so be careful when we do this kind of combination. And it's called the quotient group or the factor group. Or factor group. And so if you use just exactly this definition, since we have seen that 4Z has 4 cosets in Z, indeed this gives you the 4 elements of your factor group here. And so here, indeed, here, if you look at this, so this can also be understood as using the notion of equivalence, okay, equivalence class. So the notion of coset is really related to the notion of equivalence class, but we're going to come back on that. So is that here? What is the factor group? Okay, so I know it's a lot of definition. Yeah.
A group under what operation?
Sorry?
A group under what operation?
If it has one operation?
It is a group, right?
Yeah.
This is a factor group under what operation?
On the addition.
Okay.
Yep.
So what is the addition in this case?
So here, this means that the operation here that we... So the group is a set and an operation. And here, the operation you're considering is just the addition of number. And you see that here, the way we define the coset... sorry, that's this one. Here, we define then, so this is a subgroup of this with the addition, okay? And so then the cosets are given by, so here you see that I'm using this notation where you look like a multiplication, but it's really the group multiplication, meaning that it's the operation you're considering for your group. So here, the operation we're considering for the group is the addition. That's why here, when you write your coset, if you write them explicitly using the addition, it's, you use this new notation, you see? And so here, what does it mean? This means that you take all this coset where you vary G in your group you started with. And here, your group you started with is the whole group of integer with the addition, and we have seen that we only have 4 cosets, because then the other are, if you look at this one, you can look what it is explicitly. It's exactly this one. So you go back to your, okay? And so by definition, the factor group or the equivalence class here is just given by these 4 elements, okay? This element of, so here explicitly, what does it mean? This means that you take the element of Z, the integer, that as you build all the coset. Yeah?
Does the operation for the cosets always give you back the original group? As in, if it was a different
you mean here?
Yeah. Like, are all the cosets under the operation?
You mean if it's a finite set? If it's always a finite set? So here, no, it can be infinite dimensional also. Okay. So here it's because we are talking about discrete also group. So we have this kind of.
So you could have an infinite number of cosets.
Yeah. Yeah.
Are all subsets of subgroups going to be invariant normal subgroups? Excuse me, subgroups of
If you're so sorry, what is your question?
Sorry, are all of the subgroups of abelian groups going to be invariant normal? So then you
So-
could make a factor group out of it.
Yeah.
Yeah. Okay.
Yeah. Good. Yeah.
So you can. Okay.
Yeah. In case of abelian, yeah, it's you get invariant subgroup, so then you can do a
So
cosine.
you can make a factor group
Yeah.
out of like any of them. For,
Yeah.
Okay.
Yeah.
So, just to be clear, the quotient is a set of groups, right?
No, it's a set of element G that you write here.
It looks like you're applying the element G on the group H, and you're getting another group.
So here, you take all the element G that form the coset, the different coset, okay? And this gives you your.
But yeah, it's just, I think it's like it's a group of groups. So what is meant by addition is the new.
No, so here you consider your coset as an element now,
Yeah,
okay?
exactly, yeah.
But then, indeed, at the end, what you have here, it's only this 4. Okay, you don't write explicitly.
But I mean, in the general case where it's not the zero process, how do you describe the group operation?
How do you?
Um,
So this is the notation because you have the feeling that here I'm considering a set of group,
yeah.
whereas I'm considering a set of element here, okay, of this group. So maybe the notation is not.
So you have a group where the elements are groups, right?
Is it more accurate to say that it's G such that G of H is a coset? It looks like the G of H is the element, but it's just the G is the
Yeah.
element of group, right?
Yeah. So maybe, yeah, you want to read. Maybe I can think about a notation using more the kind of equivalence class. Maybe it would be more clear to you. So here, yeah, it's a group. It's a set of element G that you have your coset, the coset of H in G.
Yeah,
Okay.
But that's a set of that's not a set of groups. That's a set of elements of groups.
Yeah.
Right?
Okay. Is that more clear or not yet?
So it's the union of all of the set of all the groups GH.
Not all the groups.
Or the
I
element?
don't understand.
It's not all the groups because you take each element of H and you multiply by G,
Right.
and
So-
that's going to give you another element.
Right. Do you do it for all G, or is it just one specified?
No, it's for all G. So here for the coset, your G is fixed. And now once you have your coset, you can build your. Okay. Yeah, Lila.
Okay, so my understanding is that GH is all the elements of H multiplied by G. So that thing you have written on the right-hand side of the equation, is that all the set of all the cosets, or is that one coset for a specific G?
No, so it's all the element G that as you have a different coset. That give you. Okay. Yeah. So let's. Yeah. So here, what you at the end, it's a group. Your group is a group of elements. Okay. Of your starting group. It's not a. And yeah. So maybe it's not.
All I really wanted to know is if that was the collection of the coset groups.
Yeah. So.
I think everyone's asking the same question. Is the quotient group made out of cosets of the original group, or is it made out of elements of the original group?
But at the end, yeah, at the end it's the same. At the end, you end up with element of the group. Okay, but if you build here all your coset group, you look at what are the elements inside your group, and then the only different one will be. Okay. So in fact, it's here the same. I know the notation. Yeah.
It could be rewritten G in big G such that GH is a coset of G.
Yeah, I think it would be equivalent. So I need to check. Yeah. Okay.
it's always the case that you have the same number of elements there and the same number of cosets.
Yeah.
Right.
Okay, so I'm going to, since it's not, I'll let you think about this, okay? And during the tutorial, if you want, we can go back on this definition if it's not clear. Okay, any more questions here? So here we haven't talked at all about groups that we're going to use in physics yet, but even with that, already at this level, a very important tool is going to be the theory of group representation, okay? Because a lot of what physicists are going to use to extract information from symmetry is not going to be the group itself, themselves, but the group representation, okay? So let's first start with having a look at what is a group representation here. Okay. No, I don't need this one. So this is the second part. The first part was the introduction, and here we're going to have a first So again, I need to start with the definition. What is a representation? Okay. So a representation of a group G is going to be a mapping of the element of G onto a set of linear operators with the following properties that I'm going to of linear so with the following properties. So which are that you want, of course, that the identity of your group is the identity operator in the space on which the linear operator are going to act. Okay, so this is the identity on your group, and it's going to be the identity represented as the identity operator in the space on which the linear operators are going to act. And you also want to have this property with the multiplication, meaning that, so here, the multiplication between your linear operator, the group multiplication law is mapped onto the natural multiplication in the linear space on which the linear operator acts. Okay? And in fact, what we're going to use for us are going to be mostly matrix representation. So indeed, you're going to talk about matrix multiplication. So let's just focus again on this simple example, okay? So let's put that on the back. So we have just defined what is a cyclic group. And in fact, cyclic finite groups are one of the family of finite group. Okay, there are 5 families. So one are the cyclic groups for finite groups. So I'm just going to keep this table here. And cyclic finite groups are, so if I have n elements, usually we're going to use this notation. So Cn are what we denote the finite cyclic group with n elements. And usually they represent, so here it's a cyclic notation for a cyclic group. And they represent the symmetry of the propellers with n leaves, okay? So with this rotation. But so here, we already looked at two examples of the cyclic group C4, okay? In the case n is equal to 4. This is a table, the multiplication table for C4. So if now we go to the abstract level, okay? So here explicitly we give that what was in terms of these two sets of numbers, but if we remain at the abstract level, this is what we call the cyclic group with this table of multiplication where the binary operator here is not specified, okay? If it's so what would be a representation of C4? Here you can check that, of course, again, the identity has to be number 1, but then we could represent A so this is just I. Then you understand that we are on the cyclic. And so here we get minus I. So this is a representation of C4. And what is the dimension of this representation here? So here the dimension of a representation is the dimension of the space on which it acts. So here, what is the dimension of this representation?
1.
Yeah, okay. So this is a one-dimensional representation of C4. This is just a one. But of course, you don't have a unique representation for any groups. So let's have a look to another one. And see, because this one we cannot say a lot because it's one-dimensional, so there is not much to say about it. So let's look at another representation that we are going to call the regular representation, which is also an important representation for discrete group. So let's introduce the regular representation here. So here it's another representation of C4. So again, the identity element has to be the identity for the in the space on which the linear operators are going to act. Okay, so here it's going to be R4. And then I'm going to have 4 4x4 matrices. So then I'm going to let you know how you can build that. It's a very, or maybe you can already guess, how you can, just from the multiplication table, how you get this representation. Zero, zero, zero. And then the last, the last element. And so this representation here was, so this is just another example. And it was just built directly from the table multiplication here. So here, what is the procedure to follow? So you take the group's elements themselves to form an orthonormal basis for a vector space defined with your vector E, A, B, and C. Okay? And now you define G1 acting on is equal to so just using this, you can check that. So as an exercise, show that this is indeed is a representation. And here, so how these matrices are built here, you just, so if E1 is just E, E2 is just A, and then, so you define your orthonormal basis. Then you just get that the matrix element here of are given by I. And this is what is called the regular representation. So the dimension of the regular representation is going to be the order of the group. Okay? And so you can note that, in fact, this construction of the regular representation is completely general for any finite group. And so for any finite group, you can define a vector space in which the basis vector are labeled by the group elements. Okay? So of course, this is valid for finite group. And then this equation then will define the regular representation. So you see that, indeed, we have several representations for a given group. So here I already gave you 2 representations. So, but we will see that in physics, in particular in particle physics, we are mostly interested with what we call irreducible representation. Okay? So what are irreducible representation? And first, since we have several representations, you can already see that here we have 2 representations, we have several representations. How can you distinguish representation from one another? Are they equivalent or inequivalent? What does it mean? Okay? So let's just, oh, but it's already almost time for you to. Yeah, so I'm just going to give you quickly what this means to be equivalent or inequivalent and irreducible representation, and then I'm going to let you go with questions. Okay, a small exercise. Of course, I guess during your lunch break, you're not going to think so much about it, but if you have 2 minutes, you can think about it, and I'm going to give you the solution during the tutorial this afternoon, okay? So let's just finish that quickly, and then I know that you want to have a break. Okay, so what is nice about group representation is that they live in linear spaces. And the great thing about linear spaces is that you are free to choose the way we represent the state by making linear transformation. Okay? So as long as the transformation is invertible, the new states will be as good as the old one. Okay? So if now I have one representation and I have an invertible transformation, from this I can build a new representation. And these 2 representations are equivalent. Okay, so here are equivalent, and they just differ by a trivial choice of bases. What is going to be quite important here are what unitary representation. And so just to make sure, unitary operator, such as, so are going to be particularly important in physics, and we say that the representation is unitary if all the DGs are unitary, okay? And you can check that both the representations we discussed for C4 are unitary here. So now a representation is going to be said reducible if it has, so here we go back to this notion of invariant subspace. That is that the action of, so what is an invariant subspace? This means that the action of any DG here, so representation here that you have of on any vector in the subspace is still in the subspace. Okay? So in terms of a projector, we can write a projector onto the subspace. So projector so I'm going to denote this projector P. Then this means that you have something like so this exactly means that here the representation DG has an invariant subspace, and this subspace is defined by this projector P here. Okay? So, of course, a representation is going to be said irreducible if it's not reducible. Okay? So this is just the definition. And we said that a representation which is completely reducible if it's equivalent to a representation whose matrix element can be written in block diagonal form. Okay, so equivalent if equivalent to a matrix which can be written in a where, of course, these are matrices, are square matrices with dimension di, and then you want that the sum of the dimension is equal to the dimension of the representation.
Wait, A1 are, the A's are also matrices?
Yeah. So here it's so AI are di times di matrices. And then you want that the sum of the di is equal to the dimension of your representation. Okay, you started with. And in fact, here what you are doing is that you are decomposing your original representation into a direct sum of irreducible component. Okay, and you are going to see that in the example here. So using this regular representation here. So I just give you the questions, and then we're going to go back on that at the beginning of the tutorial this afternoon, so you have some time to think about it. I don't ask you to don't have lunch to solve that, but just to think about it a few times. So what is the questions? so you can check that. So this, you consider this regular representation of C4, so exercise, and so this regular representation has an invariant subspace projected on by the projector here defined. So it's a 4x4 matrix with only, since you can check that for any G, here dg P is equal to P. So indeed it's defined an invariant subspace. So the question is, what is the invariant subspace? And what is the restriction of the representation to this invariant subspace? And the last question is, in fact, any representation of a finite group is going to be always completely reducible. So now if you take S is equal to, so this is, S is the transformation I'm going to use to go to an equivalent representation, okay? So if you use S defined as this 4x4 matrices with some, it's a complex one. So I'm just giving you that. So using this transformation shows that the representation, the regular representation is completely reducible. Okay, so this is your question. You can think about at least how to show that and what does it mean exactly. Okay, so thanks. Sorry for the delay. Have a good